According to a 2015 study on the World Energy Outlook by the International Energy Agency, it's predicted that at our current rate of consumption, oil reserves will run out in 53 years, natural gas in 54, and coal in 110. Global fossil fuels usage has doubled since 1980, and it shows absolutely no signs of stopping. Thus, it is imperative to find additional renewable sources of energy. Solar power is a promising alternative, but its main limitation is a lack of consistent power generation. To help mitigate this issue, we created a prototype that both absorbs reflected light and has dual axis sunlight tracking. We made our solar panels set up mobile so it could quickly travel from surface to surface and take measurements effectively. First, we investigated whether solar panels could generate energy from reflected light, and if its reflection depended on the surface used. To minimize the effect of direct sunlight on energy generation, we performed this experiment in a dark room with no other light sources but our flashlight, which acts as the sun. The flashlight was held at an 80-degree angle from the ground, simulating maximum sunlight in summer months. Overall, we found that the mirror was the most reflective material, and white paper came in a close second. By absorbing reflecting light, solar panels can capture more sunlight and generate more energy, even on cloudy or overcast days. This can make a significant difference in terms of the energy output and cost savings for solar power systems. Additionally, solar panels that can absorb reflecting light can be particularly useful in urban areas. In these areas, buildings and other structures may reflect sunlight onto nearby solar panels. This can create a situation where indirect sunlight can actually provide a significant portion of the energy output for solar panels. Second, we implemented a dual-axis tracking system to dynamically move a solar panel in responses to changes in the angle of the sunlight. We attached 4 photoresistors to our solar panel setup, and the 2 servos moved either left or right, or up or down, towards the photoresistor pairs reporting the highest voltage. We did another test using the mirror, where we varied the angle of elevation of our light source to test the accuracy of our tracking system. We used values of 74 degrees, 50 degrees, and 26 degrees to mimic the peak angles of solar elevation in Columbus during summer, fall/spring, and winter, respectively. We found that our average voltage and max voltage levels were comparable for all 3 angles, suggesting that our tracking system is sound. By optimizing the angle of the solar panels to constantly face reflected light, we can maximize the cell's energy output, resulting in cost savings. This would also keep solar panels at a more consistent and optimal temperature, resulting in a longer lifespan. Overall, the ability of solar panels to absorb reflecting light is an important factor in maximizing the efficiency and output of solar energy systems. By optimizing solar panels to capture both direct and indirect sunlight, we can increase the viability and sustainability of solar energy as a clean and renewable source of energy for the future. Remember, one photon lost is one too many.